Today we're going to be talking about earthquakes. I'm sure most of you are familiar with earthquakes, or at least heard of them before. So earthquakes are a natural geologic phenomenon that are caused by the sudden or rapid movement of a large volume of rock. So they often result in violent shaking, or they can result in violent shaking and destruction. And they are the result of rupture and slippage along what are called faults. Faults are fractures in the Earth's crust. And the reason why the rock slips along these faults is because it's undergoing what's called elastic rebound, which we'll talk about. So why do earthquakes occur? Well, first we must understand the concepts of stress and strain. So stress and strain go together. Stress causes strain. So a stress is force. It's a force that acts on something. In the case of earthquakes, the force is the motion of the tectonic plates that are being driven by mantle convection. So the pieces of the lithosphere are moving because of the convecting mantle beneath them, and that generates a force. And that force, that movement of the tectonic plates, causes the rock to deform, to change shape. And that's what we call strain. So stress causes strain. And this strain, deformation, is gradual change in shape of the rock in order to accommodate the stress. And so with a rock, it deforms multiple. It can be brittle, it can crack or fracture. In the mantle, it's ductile. We talked about this at the beginning of the semester. It can be ductile or it can be elastic. And whenever an object or material deforms elastically, what happens is energy is stored in the object. It's called elastic potential energy. It's like when you stretch a rubber band, the further you stretch it, the more energy is stored in it. And when you let go, it snaps harder back. So whenever a rock deforms elastically, elastic potential energy is stored up in the rock. So the stress is the force causing deformation, and that is the mantle convection that's moving the plates. And the strain is the deformation that develops as a result of the stress. And if this deformation or strain is elastic, elastic potential energy is stored, just like a rubber band. You stretch or deform it. All right. So here you have rock on one side and rock on another side. So these two different plates. And it looks like this is a transform plate boundary. You can see this is what the fault right here, the fracture. And this plate's moving this way, and this plate's moving this way. And the rock is stuck together along the fault. So because the rock on each side of the fault is moving in two different directions, because the rock is stuck together along the fault, the rock is forced to deform. You can see how this is straight across here, even though I can't draw a straight line. Where this is deformed. All right, this has moved up, this has moved down, and the rock has been elastically deformed. Now this takes tens to hundreds of years for this to occur, for this much strain or deformation to develop. And the more strain, the more elastic potential energy is stored up. Why does this strain build up? Well, it's because the plates are not able to smoothly move past each other along the fault. That's because they are locked together by friction. So, friction is the force between two surfaces that resists the motion, either the onset motion if they're not moving, or it resists the motion that is already occurring if they are moving. So friction just resists motion. It's a force between two surfaces that resists motion. So the strain will continue to build as long as the friction in the fault is strong enough to hold the plates together. But what happens whenever the friction is no longer strong enough to hold the plates together? Elastic rebound. Elastic rebound is whenever the rock returns to its original shape before it was elastically deformed. So the plates rebound elastically to original shape. So this plate snaps back this way. This plate snaps back this way. And all that stored elastic potential energy is released. And that energy takes the form of vibrations that travel through the earth, and that creates an earthquake. right? So now after the slippage, you see the rock is undeformed again. It's undeformed, but it's now offset, right? It's an offset. Now, what took tens to hundreds of years to accumulate that strain, that deformation, it only takes seconds to a few minutes for it to be released. So the earthquakes last seconds to a few minutes. Now this process is called stick-slip motion. And there's a YouTube video, if I can open it here. There we go. It does a good job of illustrating this. So here we have a model. All right. There we go. So we have this block that's resting on the surface. Now, the interface between the block and the surface, that's the fault. There's two sides of rock. And there's friction, right? This block doesn't want to slide because of friction. So the bottom of this block resting on the surface is analogous to the fault. Attached to the block is a spring. And attached to the spring, though you can't see it, is a string. That string is going to be constantly pulled. Oh, you can see the string, a little bit of the string right here. That string is going to be pulled at a constant rate. And what that is analogous to is the plate motion. So the constant force pulling the plates. Okay, that's what the pulling the string is. Now, because the block, there's friction between the block and the surface, whenever the string is pulled, the block doesn't want to slide, so it sticks there. So something has to give. So what gives? The spring stretches. It elastically deforms. So that's analogous to the rock deforming elastically. The further that spring is stretched, the more energy is stored in it. And eventually, the friction between the block and the surface won't be strong enough to hold it in place anymore, and that friction will be broken. And that's called rupture. And the block is going to slide. And whenever the block slides, what pulls it forward is the stretched spring wanting to contract. And so that all that energy in the stretched spring gets released and gets imparted into the block, lurching the block forward. And that's the earthquake. Whenever the friction between the block and the surface breaks and the energy in the spring is released as it pulls the block forward. Now you can see these blocks, there's a different amount of mass on top of each one. Now, why there's a different amount of mass is because the frictional force is proportional to the weight. So if we add more mass, we increase the frictional force. So the block at the bottom will have the largest amount of friction. The block at the top will have the least amount of friction. And so I hope you can see this. Okay, I don't know if you could see what all that I was explaining before, but here's the block as I was referring to. It's attached to a spring, as I was talking about, and the spring is attached to a string. And that string is being pulled at a constant rate. And so I think I was saying all that and you weren't able to see my screen. Sorry about that. But so this block has more friction, the bottom block. We'd expect it to slip the least frequently, right? Because that spring is going to have to stretch a lot before it can overcome the larger amount of friction. And so we expect this block to slip less frequently, but when it does slip, for it to slide further. For this block, we'd expect it to slip very frequently, but when it does slip, just move little tiny bits. All right, so let's see. See, this is just lurching. Finally slips, while this one is just scooting along. It's a little tiny. Let me replay that. So this one has little tiny slips that are very frequent. This one is a little bit less frequent and larger. Okay, so let's go back. Nope, not this. So you saw that more friction's in the fault, the less often it slips. But when it does slip, it slips more. So would you rather live by a fault that slips, has a lot of friction in it and slips infrequently, but when it does, it slips a lot and a lot of energy is released, or would you rather live by a fault that slips very frequently, but it doesn't slip very much? Well, I would say the former, right? Because you have a lot of small earthquakes. It might be annoying, but you're not going to have a huge earthquake that could potentially, destroy your house, kill you, or your family, or something else. So I'd much rather live by a fault that has little friction in it. So we have very frequent but small earthquakes. But in both situations, the same amount of energy is being released. The thing is, with the fault that slips frequently, energy is being released more frequently in smaller bits. Where the fault that has more friction slips less frequently, the energy is just being released all at once instead of multiple different times. So large earthquakes are usually followed by numerous smaller earthquakes. They're known as aftershocks. So aftershocks, they gradually diminish in frequency, which means they become less, there are larger periods of time between them over time, and they decrease in size also during a period of several months after the large earthquake. And there are sometimes small earthquakes that precede a large earthquake, and they're known as foreshocks. But we don't know an earthquake is a foreshock until it's followed by a large earthquake, right? So earthquake can never be classified as a foreshock until it occurs, and then a large earthquake occurs after it, and then it's reclassified as a foreshock. So there's different types of earthquakes occur due to different types of stresses, and as a result, there's different types of faults as well. And I'd like to talk about how we orient the fault. So now I usually use a piece of paper, which I guess I still can do here. So we use the strike and the dip to orient a fault. So the strike is the horizontal angle between what is due north on the compass and where the fault plane intersects the surface. It might be easier to okay. So it's an envelope. All right, so this is the fault plane. So this is the fault. This is the rock slides along this surface, this plane. So imagine this is the surface, this imaginary horizontal line. So this is all solid rock down here. Now, let's say me straight toward you. This is due north, this direction right here. Okay, due north on the compass. So what we look at is where the fault plane itself intersects the surface. So this line is where that intersection is occurring, where the fault plane intersects the surface. As the angle between this line and due north, that is the strike. So if we have, say, if we have a fault oriented like this, because this line is pointing due north, then that would be a strike of 0 degrees. As it rotates, it's hard to see because there's no depth perception in 2 dimensions. This is rotated like this. It's rotated 45 degrees. So that'd be a strike of 45 degrees. And if it was positioned like this, that is 90 degrees relative to north. So that'd be a strike of 90 degrees. 135, and then you get to back to 180, which is 0. Okay, so that orients the fault this way. Then the dip angle orients the fault this way. So the dip angle is an angle measured in the vertical plane between the surface and the fault plane. So it's this angle right here. So if we have a fault that's oriented like this, that makes a 90-degree angle with the surface, right? So that's a dip angle of 90 degrees. Where if the fault was oriented like this, that makes a dip angle of 45 degrees. Right, so the strike orients the fault this way, okay, and the dip orients the fault this way. So this is like a 90-degree dip, 45-degree dip. All right. Okay. Back to the PowerPoint. So like I said, this is due north. This angle here is the strike angle, and this is the surface. This angle here is the dip angle. So there's two types of faults: dip slip faults and strike slip faults. So dip slip faults are faults where the slip is in the direction of the dip. And strike slip faults are faults where the slip is in the direction of the strike. So first we're going to look at dip slip faults. There's two types of dip slip faults. The first one are normal faults. So for most dip slip faults, the dip angle is 45 degrees. So if I draw, sorry, it's hard to draw a straight line. So this angle here between the surface and the fault plane is 45 degrees. Okay, so that's the dip angle. So most dip slip faults have a dip angle of around 45 degrees. All right. So normal faults are the result of extensional stress. Oh, my pen. So extensional stress. So the rock is being pulled this way. Rock is being pulled this way. So what happens is this side of the fault, which is known as the hanging wall, it slides down, and this side of the fault was known as the footwall. It slides up in a reverse. Sorry, in a normal fault. Okay. So why is this called the hanging wall and the footwall? Well, because often water will seep in these faults, and dissolved minerals will precipitate out and form deposits of minerals in these faults. Minerals like gold, silver, or iron oxide, hematite, other minerals. And so they often mine down these faults. So as a miner, so if they mine this up, as a miner standing down there, to block a wall hanging over their head, this one, the block of rock hanging over their head, is called the hanging wall, and the block of wall that they're walking on is called the footwall. So that's how it got their names. Okay. And so here, if you imagine that this is, so this is kind of awkward. So this is the fault plane, right? This is the hanging wall, and this is the footwall, right? You can't really see my shoulders, but if you grab my shoulders and pull them apart, which means you're under extensional stress, tension stress, how do my hands move? See, the hanging wall, my top hand slides down, and the footwall, my bottom hand slides up. And that allows my elbows to move further away from each other. Okay, so that is a normal fault, right? Dip slip fault is a result of extensional stress. So it would be like this. It'd be pulled apart, friction holds it together, earthquake. It's pulling apart, friction holds it together, earthquake. All right. So here you can see an example of a normal fault here. See this bed of rock is the same as this bed. Here the footwall is slid up, hanging wall has slid down. The other type of dip slip fault is a reverse fault, which is the opposite sense of motion, where the hanging wall slides up and the footwall slides down, which is the result of compressional stress. So the rock is being pushed together. Oh, I forgot to mention normal faults typically occur. What type of plate boundary would you expect to find normal faults? What type of plate boundary exerts tensional or extensional stress, where the rock is being pulled apart? I feel like I'm on episode of Sesame Street or something where I'm waiting for the viewer to answer. If you said divergent plate boundary, you're correct, right? Or the rock is being pulled apart. So we find normal faults on divergent plate boundaries. Where reverse faults, the ones we have up here, once again, is dip slip, so the dip is around 45 degrees, result from compressional stress. Where do we find compressional stress? Convergent plate boundaries. Okay, so convergent plate boundaries find compressional stress. Now, we do the same thing where I have the hanging wall and the foot wall, right? If someone would come together and push my elbows toward each other, compressional stress, right? All those slip, frictions holding together, and then all of a sudden slip, frictions hold together and slip. See, so those are earthquakes, right? So the hanging wall slides up and the foot wall slides down, and in doing so, the rock is getting shorter, right? My elbows are moving closer together. So my elbows are moving closer together because we're getting pushed closer together due to that compressional stress you find along the convergent plate boundary. Excuse me. All right, and so here we can see a reverse fault where you see this bed, where it slid up or it slid down. Now that wasn't all one earthquake. That would have been a pretty big earthquake. So there was probably multiple earthquakes where, this is, both of those beds started right here. Right, just slid a little bit, more, and so there's probably several earthquakes resulted in that overall displacement. All right, the other type of fault is a strike slip fault. And strike slip faults occur whenever the slip is in the direction of the strike. So remember, the strike is how this line with the fault plane intersects the surface is oriented. So with strike slip faults, the dip angle, right, which is the angle between the surface and the fault plane, is usually around 90 degrees. And you can see here the rock is sliding. The slip is in the direction of the dip. So with dip slip faults, we have vertical motion of rock. Rock is moving up and down. With strike slip faults, we have mostly horizontal motion of rock. Rock is moving side to side. And so this is the result of shear stress. So where do we find shear stress? Transform plate boundaries. So we find strike slip faults along transform plate boundaries. Now this is a right lateral strike slip fault because if you can imagine yourself, erase. Oh, you know what? Erase all ink on slide. Imagine yourself standing here with 1 foot on one side, 1 foot on the other side, right? It's the rock on the right-hand side that moves towards you. Even if you turned around and you were facing the other way, it'd be the rock on the right-hand side that's moving towards you. Actually, this person does a better job than my stick figure. Cut this person here. So this is a right lateral strike slip fault where you can see the rock on the right side is moving toward them. The rock on the left side is moving away. If this gentleman turned around and was facing the other way, this would be his right-hand side. This rock would be moving toward him. Right, so the rock on the right-hand side moves towards you, the rock on the left-hand side moves away. So the other type of strike slip fault is the same thing, just the opposite sense of motion, where the rock on the left-hand side moves towards you, the rock on the right-hand side moves away. All right. So here you can see some strike slip faults that actually came to the surface, or the fault planes came to the surface. You can see this motion. So this fence used to be a straight line, and then every time there's an earthquake, this side moves that way a little bit, this side moves this way a little bit, and all these posts fall out on the ground. The cows get out. The farmer is a big pain in the butt trying to wrangle all the cows back in. I don't know, cows, sheep, whatever. And they used to, put a little bit longer members in here, right, to accommodate this now larger offset, right? So that's annoying, right? That's annoying. Every time there's a little earthquake, oh, the cows got out. Right? So this one, you can tell this earthquake, this fault doesn't rupture too often. This road used to be a straight road. And this was the fault. And so this road was actually built on deformed rock. So this rock was deformed this way, and this rock was deformed this way. Because the plates want to move. The plates are moving this way and this way, but because the plates were stuck along this fault, they couldn't. But whenever this fault, fault ruptured, this rock would elastically rebound, and it moved that way. And so you can see how the rock was deformed, right? You can see it's undeformed. So whenever this road was over here, that was it being deformed. But that's some substantial offset, right? That's a couple of feet it moved. So that was probably a decent sized earthquake. So now, whenever an earthquake occurs, energy is released, and a lot of the energy is in the form of seismic waves, which are vibrations that travel through the earth. Now, there are two types of seismic waves. Body waves, those are waves that travel through the interior of the planet. And there are surface waves, which are waves that travel, as their name suggests, along the surface of the planet. Now, first we're going to look at body waves. There's two types of body waves, P waves and S waves. You can think of P waves, the P for primary, because they're the fastest of all waves, and they're the first wave to arrive at any location on Earth after an earthquake, hence primary. They move as a push-pull wave, which is an alternating pulses of compression and extension in the rock, or they can travel through liquids, because all materials can be compressed and expanded. So it's almost like a slinky. If you have a slinky at one end fixed and you hold the other end, you give the slinky, you push it really quickly, the coils right in front, they compress. And if you pull it back really quickly, the coils, you have these compressed coils from the rapid forward push, and you get these extended coils from the rapid pull back. Now that zone of compressed and extended coils, that travels or propagates through the slinky as a wave. That's like a P wave. A sound wave is just like a P wave, where it's compressed and expanded air molecules that travel through. So P waves are just like sound waves, and they can travel through solids, liquids, or gases. And so here is the particle motion of a P wave. I have that up here in Google Chrome. Not here. I'm going to get out of this. It's a very young Drew Barrymore there. So here you can see the wave is going to travel in this direction. Oh, I can't draw on this. That's right. The wave is going to travel in this direction. And if you pay attention to this region of the rock, the material that's highlighted in black, you'll see how it deforms as the wave passes through. So it gets compressed and then expanded as the wave passes through. So the particle motion, the way the particles of the rock move, is back and forth, parallel to the direction the wave is traveling. So that's a P wave. Okay. New share. The other type of body wave is an S wave. S for secondary, because it's the second wave to reach any location after an earthquake. Now they are transverse waves, which mean they don't move as a push-pull, but they move as a shearing or shaking of the particles at perpendicular angles to the direction the wave is traveling, like shaking the end of a rope. If you have a rope attached to one end, and if you give the rope a good up and down shake, you get this pulse in the rope that then travels through the rope. If you pay attention to any particle of the rope, as the wave passes by, the particle goes up and down, perpendicular to the direction the wave is traveling. You can even do it side to side too. Instead of moving the rope up and down quickly, move side to side quickly. But because they're shear waves, they can only travel through an object that wants to retain its shape, which are solids. So S waves can only travel through solids. All right, so we're going to see an S wave here. So you can see the particle moves up, the particle motion is up and down, perpendicular to the direction the wave is traveling. You can see the material is not compressed or expanded at all, it's just sheared, just deformed. Okay. Okay, so those are the two types of body waves, P waves and S waves. Then we have surface waves. So surface waves are nothing but, there are a bunch of body waves, like P and S waves, that travel along the surface. And what happens is they interact with each other to create these larger waves. They interfere with each other to create these larger waves. They're known as surface waves that travel along this surface. So surface waves are just a bunch of body waves interacting with each other along the surface. So one type of surface wave is a love wave. Now it's a bunch of S waves where the motion is horizontal, but side to side, perpendicular to the direction the wave is traveling. So if this wave is traveling in this direction, the motion is side to side, back and forth, perpendicular to the direction the wave is traveling. And they travel faster than the other type of surface wave we haven't talked about yet, Rayleigh waves. But because love waves are just made of S waves, they cannot travel through air or water. They can only travel through solids. And so here we'll see a particle motion of a love wave right here. So you see how the surface oscillates side to side, perpendicular to the direction the wave is traveling. That's a love wave. So you can imagine love waves are pretty destructive to structures in the event of an earthquake. Then Rayleigh waves are a combination of P waves. So P waves, remember the motion's back and forth, parallel to the direction the wave is traveling. And then vertically polarized S waves, so up and down motion, perpendicular to the direction the wave is traveling. So the back and forth, up and down motion result in this elliptical motion. And so it's like this rolling or rippling of the earth. And it's almost like the waves on water. Those are Rayleigh waves. So because they have P waves in them, Rayleigh waves can travel through water. And here we'll look at some Rayleigh waves right here. So you can see there's a combination of both back and forth and up and down motion. And it looks like just like a water going through, a wave going through the water. That's a Rayleigh wave. Okay. Oh. So we learn about Earth's interior structure using seismic waves. We measure seismic waves using an instrument called a seismometer. So what we do is we go out somewhere where it's very quiet, right? So far away from people. We dig a hole in the ground. We put one of these large plastic drums into the ground. And we backfill it. We dig a hole and you fill the dirt back in. And you pour some concrete at the bottom. And you place the seismometer on top of it. And you put the lid on it. You seal it up. And it records vibrations. And you always record 3 seismographs. Why 3? Because you want to record motion in the north-south direction. That's 1 seismogram. You want to record motion in the east-west direction, and then that's another seismogram. And then the third one is you want to record motion up and down. So that's the third. So you have all 3 dimensions. You have the vibrate motion in all 3 dimensions: north, south, east, west, and up and down. So these seismograms, they tell us a lot about Earth's interior. Actually, it wasn't until we had until seismology that we knew what the interior of the Earth was like. So why did we not really understand the Earth until the 1960s and 70s, it's because we really only started to learn more about the Earth through seismology, the interior structure of the Earth through seismology until then. So as a seismic wave travels through the Earth, what happens is it bends back up to the surface. That's called refraction. Why does it bend? Because whenever a wave goes from one material into another, if the speed at which the wave travels is different in those materials, the wave bends. Just like how this light wave, it bends as it goes from the water to the air. And that's why it looks like this straw is discontinuous. It's because your brain thinks that the straw is where it's located in the direction the light is coming from. But actually, the light is bent on its path from the straw to your eye because it bends when it leaves the water and enters the air. Same thing with corrective lenses. What do corrective lenses do? They bend light, they refract light so it focuses properly on the back of your eye and your retina. And waves, they bend toward the slower material, okay? So, and wave speed is seismic wave speed is proportional to density. So because these waves bend back up towards the surface, that means they're bending towards the lower density material. So that tells us that density increases with depth. And we also see waves that bounce off of interfaces, and so those are different layers. So these are refractions, these bent waves, and then reflections are waves that bounce off. And we can use these reflections to see the different layers in the Earth. Actually, the first major discovery from seismology was that the Earth's outer core was liquid. Because remember, S waves can't travel through liquids, they can only travel through solids. So after an earthquake, it was observed, so here's an earthquake, it was observed that no S waves were recorded on the other side of the planet after an earthquake. Why? Because the Earth's outer core, being a liquid layer, casts a shadow on the other side of the planet because S waves can't travel through it. That's one of the first major discoveries. Now, interestingly, seismology got its birth through nuclear weapons. So whenever nuclear weapons were developed in the 1940s, and as other countries began to develop the ability to construct nuclear weapons, they were testing them. And then there was a nuclear test ban treaty put in place, fortunately, that you could no longer test nuclear weapons. So, but how could you get around this? Well, you can't detonate a nuclear device above the ground to get away with it. There's a huge mushroom cloud, you have nuclear fallout, radiation is detected. So what would people do? What would nations do? They would dig a big hole and detonate it underground. So the only way to monitor subterranean detonations is to listen for the vibrations. And so that was the first major deployment of seismometers, was to enforce the nuclear test ban treaty. And this was, a couple decades after the 40s, so in the 50s and 60s. And unintended consequence of that is that they had all this data. They not only recorded underground detonations, but they also recorded vibrations from earthquakes. And the geologists, the seismologists, looked at this data once it was declassified, like, oh wow, we can learn a lot from Earth's interior from this data. So they started developing better, more sensitive seismometers and deploying them all over the planet, listening to earthquakes all over the planet. And so we use seismic waves that travel through the Earth to image Earth's interior, just like we use light waves that travel through our bodies to image the interior of our bodies, like in a CT scan, or a CAT scan, or an X-ray. Right? It's called seismic tomography, and it's using seismic waves that we image the Earth's interior, so we know what the internal structure of the Earth is through seismology. So there's an earthquake, right? And so looking at seismograms, we measure the distance from the earthquake. So say this is the earthquake right here. We measure the distance in angle. And that angle is the angle between a line that connects the location of the earthquake to the, where's my pen? Oh. from the location of earthquake to the center of the earth to where the seismic wave is observed. So for example, this is 90 degrees. This location is 90 degrees from the earthquake, where the opposite side of the planet is 180 degrees from the earthquake. And so here we have distance from the earthquake in degrees, and then this is time after the earthquake. You can see different waves arriving. The further you are from the earthquake, the later they arrive in time. Hold on, Lauren. And so because the seismic wave speed is proportional to the density, we can map out the speed, the seismic wave speed, as a function of depth in Earth, and therefore get the density of Earth as a function of depth. And this allows us to construct models of Earth's interior. So prior to seismology, we had no idea what the internal structure of the Earth was. And that's what, one of the ways that we came to understanding of plate tectonics is once we had this clear picture of the internal structure of the Earth, we understood the size and nature of layers like the asthenosphere and the mesosphere. We could put that information together with the observations at the surface of plates moving, locations of earthquakes, volcanoes, together as plate tectonics. This is a very interesting figure. So this is surface waves. These are surface waves that were recorded after the 2004 Sumatra Andaman earthquake that created the Indian Ocean tsunami. And so this is time in minutes after the earthquake on the x-axis, and this is distance in degrees from the earthquake. And as you can see, the further from the earthquake, the later the time the waves arrive. So this wave is called R1. So this is the Earth. This is the earthquake. R1. Those are waves that were recorded as they traveled along the surface. R2, you see, has the opposite pattern, where the closer the wave is to the earthquake, the later in time it arrives, and the further it is from the earthquake, the earlier it arrives. That's because those are waves that traveled around the planet and then were recorded on the other side on their way back. And then R3, this wave, this is R1, that circled the planet, was recorded, came around and was recorded again. And R4 has the same pattern as R2. Those are waves that went this way, recorded as R2, came all the way around and recorded again as R4. So you literally see seismic waves going around the planet multiple times after this large earthquake. So we also use seismic waves to locate the source of an earthquake. So P waves travel faster than S waves, about 1.7 times faster on average. And so the further from the hypocenter we record seismic waves, the larger the lag time between the P and the S wave arrival. So if you think about a race, like a foot race, or any sort of race, but if you think of a foot race, everyone starts at the starting line, right? And the starting line is like the earthquake, but some runners are faster, some runners are slower. And when the race starts, all the runners are close together. But as they continue, the faster runners, they move out in front, and the slower runners fall behind. So the further along the race track, the larger the space between the fast runners and the slow runners. And so if you're standing at any point along the track, and if you're recording the arrival time of the runners, the delay between the fast runner's arrival and the slow runner's arrival is going to be larger the further you are from the starting line. And that's what happens with P and S waves. So this delay time between the P and the S arrival, that is a function of distance from the earthquake. So the further you are from the earthquake, the larger that is. So here, this plot here, we have distance on the x-axis, And we have time in minutes that the wave arrives on the y-axis. You can see the further from the earthquake you are, the later in time the P wave arrives. And the further you are from the earthquake, the later the S wave arrives. But the delay time between the P and the S wave, it increases. You can see it increases as you get further from the earthquake. Okay, so say, for example, we have 3 seismograms recorded from after an earthquake at 3 different locations on the planet, and each of these red lines represents a minute in time. So here's the P wave arrival. We have 1, 2, 3, 4, 5 minutes. So there's 5 minutes between the P and the S wave. Over here in this graph, it's at this distance right here that there's a 5-minute delay time between the P and the S wave arrival. What does it mean? It means that the earthquake occurred at about 3,400 kilometers from Nagpur, India, where that seismogram was recorded. So what we do is we plot the location of that seismogram on the map, and we draw a circle with that distance as its radius. So in this case, 3,400 kilometers. Because we know that the earthquake occurred 3,400 kilometers away from that seismogram. So the earthquake could occur anywhere on that circle. We still have an infinite number of locations, potential locations for the earthquake, any point on that circle. What we do is do the same thing for another seismogram, say Paris. We measure the time delay between the P and the S wave, and that gives us a distance. We plot a circle whose radius is that distance, and that intersects, those 2 circles intersect at 2 locations. So now we have 2 potential locations for the earthquake. Then we do a third seismometer, repeat the same pattern, draw a circle whose radius is equal to the distance the seismometer is from the earthquake, gathered from the delay time between the P and the S wave. And we see we have 1 unique intersection, and that's the location of the earthquake. Now this process is called triangulation because we use need three seismometers. Triangulation isn't unique to seismology. We use it for everything. It's how the position of your phone is determined. It communicates with 3 different cell phone towers and it triangulates your position. GPS works the same way. A GPS communicates with at least three different satellites. It's able to triangulate the location. So that's how we determine the location of earthquake. Now, this process is automated. So whenever an earthquake occurs, computers analyze the seismic waves and are able to analyze multiple seismic waves from different locations and calculate the location of the earthquake very rapidly. So where the location of earthquake occurs, it's called the hypocenter or the focus, and it's the actual point in space where the fault began to rupture. Right? So the hypocenter is actually the actual location of the earthquake. If we project the hypocenter up to the surface, that's called the epicenter. Okay, so the epicenter can be reported just using a latitude and longitude, but the hypocenter needs a latitude and longitude in a depth. Right? Now, the size of an earthquake, we used a magnitude scale. So for a long time, we used the Richter scale, which a lot of you might have heard of. The Richter scale is based off of the amplitude of the largest seismic wave recorded after an earthquake. It's a logarithmic scale, which means each increase of the Richter scale by 1 corresponds to a 10-fold increase in the amplitude of the seismic waves. So what that means is a magnitude 4 earthquake on the Richter scale, the shaking was 10 times greater than the magnitude 3 on Richter scale. Magnitude 5 earthquake on Richter scale's shaking was 10 times greater than the magnitude 4's, or 100 times greater than the magnitude 3. So each increment of 1 on the Richter scale corresponds to a 10-fold increase in the amount of shaking. Right? So that makes a big difference because the difference between a 6 and 7 magnitude earthquake on Richter scale is much smaller than the difference between a magnitude 7 and an 8. Right? And the energy released by an earthquake on a Richter scale, there's roughly a 32-fold increase in the amount of energy released. So, for example, as far as shaking goes, a magnitude 5 earthquake on Richter scale has as much shaking as 10 magnitude 4's, or 100 magnitude 3's, or 1,000 magnitude 2's. Magnitude 8 Richter scale has as much shaking as 10 magnitude 7s, 100 magnitude 6s, or 1000 magnitude 5s. And here's the energy equivalence. It's roughly a 32-fold increase. So energy released by a magnitude 8 earthquake is the same amount of energy as releases 32 magnitude 7s, or 1024 magnitude 6s, or 32,768 magnitude 5s. A magnitude 7 earthquake is not a small earthquake. So a magnitude 8 earthquake is really, really powerful and energetic. And then imagine that a magnitude 9 earthquake has about 32 times the energy as a magnitude 8, and 10 times the shaking as a magnitude 8. So magnitude 9 earthquakes are extremely large earthquakes. We don't use the we don't use the Richter scale anymore because it goes off of the amplitude of shaking, the seismic waves, which is subjective, because the shaking that results from seismic waves is dependent on the type of material, if it's loose sediment or if it's bedrock. So if you measure a seismic wave, say at the bottom of a valley in sediments, and look at those seismic waves, that would give you a different size for the earthquake than if you measured the seismogram from the same seismic wave from the same earthquake on a ridge in the bedrock, because the shaking would be smaller, so it'd give you a smaller size earthquake. So that's subjective. We don't like that in science. So what we use now is the moment magnitude scale, which is objective. And we calculate it by calculating the amount of slip on the fault, what length of the slip ruptured, that's what that is, the area of the fault that slipped. So what is the area, what is the surface area of the fault that actually slipped? And then we multiply that by the strength of the fault that ruptured, basically what the force of friction that was in the fault. So it's how long, what length of the fault ruptured, what area of the fault ruptured. We multiply those two, and then we multiply it by the strength of the rock. That gives us the amount of energy released by the earthquake, and that's the moment magnitude. So this figure shows us earthquakes and energy equivalents. So this is the moment magnitude on the left-hand side here. And on the right-hand side is the equivalent energy release in terms of kilograms of explosive, TNT. So what does that mean? Magnitude 2 earthquake releases as much energy as 56 kilograms of TNT if it was detonated. Right, so a magnitude 9 earthquake releases as much energy as, what is this? That's a million billion, 1.8 trillion kilograms of TNT. So it's a lot of energy. So here we have a description of the earthquakes, right? So magnitude 2 are very minor earthquakes felt by humans. 3 minor earthquakes felt by humans. 4 light earthquakes, some property damage. 6 minor earthquakes, property damage. 7 are very strong earthquakes, billions of dollars of damage, loss of life. 8 are great earthquakes. There's a severe economic impact, large loss of life. And magnitude 9 earthquakes are the largest recorded earthquakes. They're destructive over a large area and a massive loss of life. We have notable earthquakes, and they're plotted at their respective magnitudes. So this 1960 Chilean earthquake is the largest earthquake we've ever recorded. And the center column is the frequency. How many earthquakes of that magnitude occur per year? So we have about 1 million magnitude 2 earthquakes, say 1,500 magnitude 5s, 150 magnitude 6s, 18 magnitude 7s, 1 magnitude 8 per year, and less than 1 magnitude 9 per year. So we have magnitude 9 earthquakes not every year, like maybe every 3 or 4 or 5 years. But over here we have plotted other events and their equivalent energy. So the energy of the average tornado is a magnitude 4 and change earthquake. The energy released in the Hiroshima atomic bomb detonated over Japan in the Second World War released the same amount of energy as a magnitude 6 point something earthquake, right? So it shows you, maps the equivalent energy of different size earthquakes to other events. So where do earthquakes occur on Earth? So most earthquakes occur at plate boundaries, right? And we can actually map the plate boundaries by mapping the locations of earthquakes. But what depth do they occur? So earthquakes result from elastic deformation. So when the rock is deformed, like say this material, it's squeezed, it's deformed. elastic if stress is relieved and it returns to its original shape. Now that's the lithosphere. The lithosphere deforms elastically. However, the asthenosphere, it deforms ductily, where if you deform it, change shape, it remains permanently deformed. It doesn't return to its original shape. So therefore, earthquakes cannot happen in the lithosphere because that elastic potential energy is not stored. Right? It's not stored. So earthquakes cannot happen in the asthenosphere. And the thickest lithosphere is lithosphere where there's mountains, and it's about 100 kilometers thick. So in theory, basically, earthquakes can only occur up to a depth of about 100 kilometers. So here we have a map of locations of earthquakes, but their depths are color-coded. So the blue ones are shallow earthquakes. They occur at depths less than or equal to 60 kilometers. About 85% of earthquakes occur at those depths. Intermediate depth earthquakes, those are the yellow ones, but it's in black font down here so you can see it on the white. Those are 60 to 300 kilometers depth. That's about 12% earthquakes. And deep earthquakes are those at depths greater than or equal to 300 kilometers, about 3%. You can see most of these deep earthquakes, they occur along subduction zones. So here, South American subduction zone, and there's subduction zone trenches there. We have all these trenches. Oh, the trenches on the other side there. And so, but we said that, you know, earthquakes only occur in the lithosphere, and the thickest lithosphere is about 100 kilometers thick. But how are these earthquakes occurring at such large depths? Well, to explain that, we can go to our earthquake browser. So this allows us to look at earthquakes plotted on a map, and it color codes them with respect to depth. Now let's look at, say, South America, a place where we saw some of those deep earthquakes. I want to plot a lot of earthquakes. Let's plot 3,000 earthquakes. All right. So now you can see here's the color scale over here. So depth, so purple is 0 to 33 kilometers, blue 33 to 70, green 70 to 150, yellow 150 to 300 kilometers depth, orange 300 to 500 kilometers depth, and red is greater than 500 kilometers depth. You see a pattern? As you go from the coast inland, the earthquakes become deeper. This allows us to do is we can look at it three-dimensionally. So here, this white line is the coast. This blue line is the trench, okay, where this plate is subducting under this plate. So this is north-south. This is east-west. I can click this and drag it and look at the cross-section. And so now we're looking at, as is up, this is down. Those deeper earthquakes, those earthquakes are occurring in the subducting oceanic lithosphere. So that's why we have these really large earthquakes. You said earthquakes that only occur in the lithosphere, which is true, but at subduction zones, the lithosphere sinks down into the mantle. And we see earthquakes continuing to occur in the lithosphere as it subducts down beneath Earth's surface. So these earthquakes up here are earthquakes occurring in the overriding plate, the overriding lithosphere. This is earthquakes occurring in the subducting oceanic plate as it goes down. So once again, here's how seismology is allowing us to view plate tectonics actually occurring. We can actually see this plate subducting underneath the other one, which is really cool. So those are called Benioff zones. So earthquakes that occur in the subducting lithosphere. So here is looking at the Indonesian subduction zone, the trench. So look at cross section along this line. You see here is the trench right here, because this is the overriding plate. These are earthquakes occurring in the overriding plate. So that's one plate. You can see here's the other plate here, subducting underneath it. So you can see the two plates, and that's the trench, right? You can see the plate tectonics in action. So this is sinking. So earthquake hazards. So we obviously have destructive vibrations, but you might be less familiar with is liquefaction, landslides, and tsunami. So destructive vibrations, the interesting thing about those is that it's not the earthquakes, the vibrations that actually cause damage or like loss of life, I should say. It's the failure of infrastructure that kills people during earthquakes. So you see, this is a picture from, I believe, Anchorage, Alaska after the 1964 earthquake. You see this structure in the background, it did not fare well. Where this structure in the foreground, it looks unscathed. What's the difference? Well, this structure is built out of reinforced concrete. Now, concrete does not give very well. It doesn't flex, doesn't bend. It can't absorb energy. So it cracks and fractures and it breaks. So here it collapsed. This structure has a steel frame, and steel is flexible. So it can oscillate back and forth. It can absorb all the energy. So oftentimes, earthquakes are most destructive in locations where they haven't built their infrastructure, their buildings, their power lines, their water lines, their gas lines to withstand the vibrations. And what happens is things fail, buildings collapse, gas lines break, electrical lines break, the shorting electrical lines ignite the natural gas, you have fires. You can't fight the fires because the water lines are broke, there's no water. Also, you can't get into where the fire is because the roads are filled with rubble. There's a complete breakdown of the infrastructure. That's what causes most of the damage. It's usually fires after an earthquake that cause more damage than the earthquake itself. But if you can build your infrastructure to withstand the shaking, then you can avoid all that destruction. So cities like Tokyo, San Francisco, and Santiago, Chile, they build their structures to withstand that vibration. So an earthquake that occurs there is less destructive than, say, earthquakes that occurs in a place like, say, Haiti. In 2010, the Haitian earthquake was completely devastating because their infrastructure was not built. Haiti is a very poor country, so they don't have the money to invest in their infrastructure, which is unfortunate. And the people of Haiti suffered because of that, even more because all their structures collapsed during the earthquake. Liquefaction is another earthquake hazard. This happens whenever we have loose, unconsolidated sediment that has water in it. Whenever you shake it, it liquefacts, which means it behaves like a liquid. You ever go to the beach and you shovel some wet sand into a bucket, and you have a mound of sand in that bucket, and then if you shake it, that mound flattens out? Well, that's liquefaction. So whenever the ground is shaken by the seismic waves, if there's loose unconsolidated sediment, it can liquefact and flow. These apartment buildings were built just on loose, they're founded in loose unconsolidated sediment. Whenever the earthquake occurred, the sediment liquefacted, and what happened is this was the building. This is the sediment. The sediment flowed out from underneath the weight of the building, and the building just toppled over. This car actually sunk down into the sediments when they liquefacted. So liquefaction is a significant hazard, especially in low-lying areas like basins, river valleys, and coastlines where there's a lot of wet, unconsolidated sediment. So in the 1989 Loma Prieta earthquake in California, a large portion of San Francisco, the Marina District, liquefacted and it just flowed right into the bay. All the structures just slumped right into the bay. Landslides are another hazard associated with earthquakes that can be delayed. So earthquake can cause the rock, so you can see there's a sedimentary rock, they develop these cracks and fractures. Over time, the rock can slide along those cracks and fractures. So you have this mass movement of material, and there's a landslide. And so you can see here's a structure that was in that which is destroyed by a landslide. So this can occur, the same time as the earthquake, or days or even years after an earthquake. Then there's tsunami. The tsunami usually occur along subduction zones where you have reverse faults. So you have the subducting plate converging with and something under the overriding plate. This creates a reverse fault, where this is the hanging wall, it slides up, the footwall slides down. But whenever the overriding plate snaps back up during an earthquake, it displaces a large volume of water, which creates a wave. Oh, you know what? I need to open that. I need to change. Okay. So here we have the oceanic plates subducting the overriding plate. You can see they're locked together. The fault's locked together by friction. So the overriding plate is being flexed down. This is taking hundreds of years, and then all of a sudden, fault ruptures. The overriding plate undergoes elastic rebound, snaps back, and some of the energy is imparted into the ocean, and it flows inland as a tsunami. Okay. So this is a video. I'm not going to watch it right now, but if you go into Blackboard and look at the PowerPoint slides, you'll see this image in the slides. You can click on it, look at this hyperlink, and you can really see what a tsunami looks like. The important thing I want to point out is a tsunami isn't this large breaking wave that comes inland, right? Like we see in the movies. What a tsunami is, it's like the water just begins to flow inland. So it's like the tide's coming in very rapidly, but it just doesn't stop. It just keeps on flowing in and in and in and in and in. Then it'll wash back out. Then it'll wash back in as the next wave comes in. And tsunamis are extremely powerful and destructive. So please look at this PowerPoint on Blackboard and watch this video. And if you want to go on YouTube and look up aerial footage of the 2011 Japanese tsunami, that's some pretty dramatic footage too. Shows how destructive tsunami can be. So earthquake prediction. So unfortunately, we can't make short-range predictions. We can't make statements like a magnitude 8.0 earthquake will occur in Los Angeles in the next 2 days. If we could save a lot of lives and property, but we just can't. We're not there yet. And I don't know if we ever will be there. We can, however, make long-range forecasts. Like we can say, for example, a magnitude 8.0 earthquake will occur in Los Angeles in the next 100 years, which is still useful because that way we can prepare all the people. We can put what's called mitigation efforts in place where they know the hazard of earthquake, what to do in the event of an earthquake. All structures that we build are built to withstand the vibrations of an earthquake. Older structures are retrofitted. They're adapted so they won't fall down. And so we can take all those steps so that whenever that earthquake does occur, it won't be as devastating. Looking at subduction zone earthquakes, which are the largest earthquakes on the planet, we can see that we map the fault. So this is the plate, it's subducting under its overriding plate. And these shaded regions are areas of the fault that have ruptured in the past. And then we have the year in which they ruptured. So this was 2007. This was 1797. This was also in 1833. This segment was in 1861 and 1907. This one, 1881, 1941, and so forth. However, you see this big green segment right here? Prior to 2004, this segment hadn't ruptured. What that means is that segment of the fault, the rock had been deforming for many hundreds of years. So elastic potential energy had been accumulating in the deforming rock for a couple hundred years, because there's never been an observed earthquake in the area. And so that's known as a seismic gap. And seismic gaps allow us to identify where the next large earthquake is likely to occur on a fault. So this was a very large seismic gap, and seismologists knew it. And they thought, oh, maybe this segment of the gap will fill in. And that's a large segment, right? If you look at a comparable segment like this one, that was an 8.6 magnitude earthquake, right? It was a large earthquake. So this would be on the same size earthquake. Worst case scenario is if the whole unruptured segment ruptured at the same time, which is actually what happened. It happened on 2004, actually December 26th, 2004, was a magnitude 9.2 earthquake. It was the second largest earthquake recorded in we've ever recorded, and it triggered the 2004 Indian Ocean tsunami, which was extremely devastating. It was the most lethal natural disaster in modern history, killing around 250,000 people, 250,000 people. Here's the subduction along the west coast of Mexico. And you can see there's some seismic gaps, right? This segment has not ruptured. This segment has not ruptured. Prior to 1985, this was a gap too, the Michoacan gap. But in September 1985, it filled in. That segment of the fault ruptured. Interestingly enough, little towns along the coast in the mountains, they were relatively unscathed by the earthquake because they were on bedrock, which minimizes the shaking. Where Mexico City is built on a filled-in lake bed, so it's built on unconsolidated sediments. It's in the ancient city of Tenochtitlan. That's where Mexico City is located, which is the capital of the Aztecs. And so it's on a built-in, filled-in lake bed. So Mexico City's on these unconsolidated sediments, which amplifies the shaking. And this earthquake was extremely destructive, killing tens of thousands of people in Mexico City in 1985. So this gap will eventually rupture, and so will this one. And so hopefully, whenever they rebuilt Mexico City, they rebuilt it to withstand this earthquake and this earthquake, because it's not a question of if, it's a question of when. Another subduction zone here, you can see seismic gaps. These areas are areas of the fault that have ruptured. You can see different gaps in there. The gap right there, that in 2011 was filled in by the Tohoku earthquake that triggered the tsunami that hit Japan in 2011. The seismic gap is useful, allows us to identify the locations in the fault where the next large earthquakes are most likely to occur. We can also apply the seismic gap method to transform plate boundaries. So this is the San Andreas fault. So this is actually the fault plane, right? This is depth, this is the surface. You can see different cities in California. So this segment of the fault, all these black dots are earthquakes. There's many earthquakes. So that means that this segment of the fault is rupturing very often. It's just creeping. It's very frequent and small ruptures, just like the small block in our our stick slip video. So it slips often but small. Parkfield, California is actually known as the earthquake capital of the world because they experience so many earthquakes. But they're very frequent but small. However, this area of the fault, this area, they don't experience significant seismic activity. So those are seismic gaps. So they'll eventually fill in. Unfortunately, they'll fill in probably with a large earthquake. There's a large amount of strain, elastic potential energy has been accumulating in these gaps. In 1989, this gap filled in. This is the main rupture, and these are all aftershocks, but it filled in that area of the fault. And so whenever they refer to the next big one in San Francisco, they're usually referring to these gaps north and south of the city. So whenever these gaps rupture, it's going to be a large earthquake. It's very impactful in San Francisco. That's our lecture on earthquakes. Thank you very much. Actually, stop recording first.